as we've already talked about L'Hopital's rule, we know how to use L'Hopital's rule, and we know that it is one of the techniques to use when we have an indeterminate form. So now we're going to, for this particular problem, we're going to see another example where we're going to use the L'Hopital's rule to find the limit of a function that has an indeterminate form. So let's consider this function here where we have f of x equals to e to the power of x divided by x squared. And we're asked to find the limit at when x tends to infinity of the given function here. So like I already mentioned, that to use the L'Hopital's rule, we need to make sure of two things. Number one, we need to make sure that the function that we're working with has an indeterminate form at the given limit. And number two that we need to make sure is we need to see that the function that we're working with is differentiable at that given limit. So from the function that we have here, we know that both of the conditions check out. It is indeed in indeterminate form, which we're going to see now, and it is differentiable at the given limit. So imposing the limit, we get e to the power of infinity divided by infinity squared. So we know that we get infinity because we know that the exponent function raised to the power of infinity gives us infinity, and this will be divided by obviously infinity as well. So you can see that we have an indeterminate form of the form infinity by infinity. So now what we're going to do is we're going to use the L'Hopital's rule to solve this limit. So I'm going to write the function here again for reference. So we have e to the power of x divided by x squared. And now using the L'Hopital's rule, we know that we need to differentiate both the numerator and the denominator separately. So given that we consider the numerator to be g of x and we have e to the power of x as g of x. So deriving it once gives us e to the power of x, and for the denominator we have, let's consider it to be h of x, and we have it as x squared. So deriving it once, we get 2 to the power 2x. So now using L'Hopital's rule, we're going to compute the limit of the function. So we have limit x tends to 2, and now imposing and evaluating the values by differentiation, we have e to the power of x in the numerator and 2 into x in the denominator. So imposing the limit, you can still see that we still get an indeterminate form where we have infinity in the numerator and infinity as well in the denominator. So this is still an indeterminate form, and we were unable to avoid the indeterminate form which we were trying to do using L'Hopital's rule. So if we encounter a situation where we face this, what we need to do is we need to use the L'Hopital's rule again and again until and unless we can successfully avoid the indeterminate form. So what I'm going to do now is I'm going to use L'Hopital's rule again. So which basically means that I'm going to differentiate both the numerator and the denominator separately one more time. So again, let's consider the numerator to be g of x. So we have e to the power of x now, and deriving it once will still give us e to the power of x. And we have the denominator, let's consider it to be h of x, and this is 2x now, and deriving it once will give us 2. So now imposing the limit again, we have x tends to, I wrote 2 here before, this is going to be infinity. So when we extend x to infinity and we evaluate the values of differentiation that we got, we put e to the power of x in the numerator and 2 in the denominator. So imposing the limit, we get e to the power of infinity divided by 2, and we know that e to the power of infinity is infinity, and this divided by 2 is simply infinity. So we got infinity as an answer. Even though we do get that, it doesn't mean that limit does not exist. The limit when x tends to infinity is infinity, and this value is valid. So what you see here is the answer that we got is no longer an indeterminate form, but we successfully solved the limit for an indeterminate form and got the answer using L'Hopital's rule.